Sketch the graph of f of x equal to x over x squared minus 1 using its domain, symmetry, intercepts, asymptotes, relative extrema, and any points of inflection. Identify the open intervals in which the function is increasing or decreasing, and concave up or down. So that's the original function. So I found out that the domain, which would you would take the bottom, is equal to, x is equal to positive or negative 1. So this is with the unity symbols, so negative infinity to negative 1, unity negative 1, positive 1, unity 1, infinity. As for the x-axis symmetry, you set the y or f of x to a negative, and you would just divide by a negative, so then that would change that, so that's not possible. Y-axis, you set the x to a negative, and when you do that, it changes the function, so that one isn't possible. Origin, you set both the f of x or y and the x to negative, so when you do that, you see that it brings you back to the original function. So this has origin symmetry. The y-intercepts, when you set x to 0, so when you set x to 0, you just get 0, so 0, 0 is the intercept. And the x-intercept is when you just set the entire function to 0. So when you do that, you also get 0, because you would bring that up, multiply each side by the bottom, and you get 0. So 0, 0 is also the x-intercept. The asymptotes, because this is this kind of function, the vertical asymptote, which is the bottom set to 0. So we found that out in the domain. So x is equal to positive and negative 1. So that's the vertical asymptotes. Horizontal asymptote is the top and the bottom. You can see that the top is less than the bottom, so that's equal to 0. If the top would have been greater than the bottom, like a greater exponent, then you would get a slant asymptote, and the horizontal asymptote would not exist. And if they were equal, you just take whatever coefficient is in front. So in this case, the top is smaller than the bottom, so y is just equal to 0. Now into the calculus, the first derivative, you take the bottom times the derivative of the top, so the derivative of x is just 1, minus the top times the derivative of the bottom. And then you divide that by the bottom squared. So when you multiply these all out, you get that. And then subtracting things, I ended up getting negative 1 minus x squared over x squared minus 1 squared. And I found out that the x is equal to positive and negative 1. You just take the bottom. You can't get anything out of the top. So I found out the relative extrema, there isn't any, because every time I checked it, it was down, decreasing the entire time. So that means that there's no relative extrema. Vice versa, if they were all increasing, then again, no relative extrema. So I just picked a point between those two. I just did negative 2 because it's closest, and put it in place of x in the first derivative, and that, helped me solve that. Same with the others. I picked a point in between. That one, obviously 0 would be the best choice, and I picked 2 for that one to check it. So no relative extrema, so no increasing or decreasing. Now on to the second derivative. Again, you take the bottom, multiply it by the derivative of the top, minus the top, times the derivative of the bottom, and over the bottom squared. So it was squared before, so then you square it again, you get a 4. And here you can see I took an x squared minus 1 out of the top here and also here, and that kind of simplified it for me. So I brought that over there, so I got negative 2x to the third plus a positive 2x minus 4x. As you can see, I get 2 times the 2x, so minus 4x times the negative 1 minus x squared over x squared minus 1 to the third power now. And with that simplified out, I got negative x to the third plus 2x plus 4x to the third over x squared minus 3. Subtracted a few things and I got 2x cubed plus 6x over x squared minus 1 to the third power. I took a 2x out of the top and I got 2x times x squared plus 3 over x squared minus 1 to the third. Again, the top, you can't get anything out of that. As for 2x set to 0 is just 0, and the bottom set to 0, you end up getting x is equal to positive and negative 1. So because x is equal to 0 and positive and negative 1, I tested the intervals between negative infinity and negative 1, negative 1 and 0, 0 and 1, and 1 and positive infinity. And here you can see I did the same thing like I did in the first derivative, only this time using the second derivative, right there. I put negative 2 in place of x for this first interval. Second interval, I put negative 1/2. Third interval, I picked positive 1/2. And fourth interval, I chose positive 2. And you can see, the first one I got concave down, second I got concave up, third I got concave down, third I got concave down, and fourth I got concave up. As for the point of inflection, I took these points that we got from the second derivative test and I put them into x for the original function. So I did negative 1 for the first one and I got that was undefined. And for positive 1 I also got that was undefined, and that is because those are the vertical asymptotes. So the only one that would work is f of 0, and I found out that that was 0 as well. So the point of inflection is at 0, 0, as well as the x-intercept and y-intercept. And you can see in the interval, like I just said before, from negative infinity to negative 1, it's concave down. See, it's concave down. From negative 1 to 0, it's concave up. From 0 to positive 1, concave down. And from positive 1 to positive infinity, concave up. So that is the graph of the function. You can see that there is the vertical asymptotes at negative and positive 1, and the horizontal asymptote at y equals 0. And the x and y intercept, as well as the point of inflection, 0, 0.